Okay.
Okay.
Dr. Juan, thanks a lot for your presence, your virtual presence in our event. We are going to start. If you please can try to share your slides just to see if it's okay. And in this meantime, I'm going to say a couple of words regarding your bio, short bio, okay? For those who are attending us, we have been transmitting this event inside our WebEx, and in this place we now we have 15 participants, and we also have a transmission in YouTube, in which we have an average of 20 people, around 20 or 40 people connecting our YouTube transmission as well. So we are going to make our event for at least 50 to 100 persons during all the transmission. Okay.
Okay.
Good morning or good afternoon. I'm not sure what is your exact time there. But Dr. Juan Gregorio Rejas is a tenured scientist at the National Institute for Aerospace Technology, and currently he's in the Space Programs Department. Dr. Juan is also a doctor in land engineering from the Polytechnic University of Madrid, UPM, and also he's an associate professor at the same university since 2003. He's an expert in geospatial analysis, image spectrometry, and anomaly detection. And today he is invited by our committee to make a speech regarding image spectrometry and active systems in the study of volcanic activity. We are very happy to have you here, Dr. Juan. Thanks a lot for accepting our invitation to make this speech for us. It's a pleasure for us, for our students who are interested in learning how you use remote sensing, how you use image spectrometry, and how you develop your work. We are starting at 9 and 10, so if you can make your presentation in around 40 minutes, so that we can have 10 minutes for questions, in case we have questions, and I'm going to show the questions for you. We can, I think that you said to some of our colleagues that you can read or questions in Portuguese, but in case you don't understand something, I'm going to try to help to make this interface with you. Okay? So feel free to start your speech. Thanks a lot again.
Okay. Bom dia. Graças aos organizadores. É prazer para mim participar deste workshop sobre computação aplicada. Hello everyone. Can you hear me?
Yes, yes.
Okay. Hello everyone. Thanks to the organization of the workshop, I am going to present the talk titled Image Spectrometry and Active Systems in the Study of Volcanic Activity. I'm going to briefly talk about a multi-source approach in the several volcanic complexes located in the central volcanic range of Costa Rica, Canary Islands, and Guatemala. The aim of this talk is to present a geospatial methodology for the analysis of the time evolution of volcanoes using different image automatic techniques compared to expert-based remote sensing techniques. We want to know what's going on in some cases when the volcanoes are close to urban areas, where are important aim will be to establish relationships that allow linking spectral patterns with what can be called as real information, and therefore identify information related to the activities entrance of the volcano. I will expose the change detection of hydrothermal alteration materials in relation with the time series from multi-sensor data acquired in spectral ranges of the visible, shortwave, infrared, and thermal infrared. To do this, we use multispectral and hyperspectral scenes from satellite data, Sentinel-2, Aster, Ali, Hyperion, and airborne sensor data, HIMAP, MASTER, AVIDIS, HSS, in a different time periods. We analyze two time series of active systems that are applying differential radar interferometry for the study of land deformation in relation with volcanic activity. To do that, we use mainly Sentinel-1 data from the Copernicus European program. This is the index of the presentation. First, I'm going to make a brief introduction from my point of view about remote sensing, data, and pre-processing. I will present results for three the study areas: Turrialba Volcano, located in Costa Rica, Central America; the Fuego Volcano, located in Guatemala, in Central America too; and the La Palma eruption in Spain that took place in 2021. Sorry. Okay, sorry. Next, I will present the previous work and the data used at the three techniques for the study of the volcanic activity that are hydrothermal alteration detection through principal components with a cluster technique and through a discrete spectral profile analysis, spectral anomaly detection, and differential interferometry SAR, and finally some conclusions. What is remote sensing? As we know, remote sensing is the science and art of remotely acquiring and processing information about the Earth and other planetary bodies without coming into direct contact with the measured object. This acquisition we can make from different platforms. Spatial provide data for analysis of large regions and extensive temporary coverage. Airborne sensors that acquire high-resolution data for specific tasks. And short range sensors used to calibrate and validate the space and airborne data, and to acquire in situ high-resolution data. In this slide, I show my vision of the detection methodological strategy and its relationship with technology. I understand remote sensing as a multi-scale strategy: large scale, medium scale, and micro scale. A strategy that feeds back and has a direct relationship with the different technologies that we can use. In my opinion, the best research results have come from a multi-source, multi-data, and multi-scale strategy. We can see in this slide the three main groups of remote sensing platforms: land platforms, cars, vans, trains, tractors, tripods, the operator himself, etc.; aerial and sea platforms, balloons, white helicopters, unmanned aerial vehicles, planes, etc.; and space platforms, Earth observation satellites, and planetary prospecting probes. And on the other hand, we have two main groups of the sensors, depending on the energy source. Passive sensors, the energy source is the sun, and active sensors, the energy source is the sensor itself. The main passive sensors are frame cameras, wishbone, and pushbone, as we can see in the slide. And the main active sensors are radar and LIDAR. We can see the different strategies to acquire data and to build imagery. We must develop data pre-processing and processing techniques in order to correct errors and to extract information from all image data, including geometric correction, radiometric correction, and a number of image arithmetic and statistical analysis. These previous steps allow us to obtain a perfectly overlapped image dataset, the identification of spectral diagnostic bands, and of the volcano activity and the accuracy of spatial correlation. As I like to say, the radiometry of the image can allow us to extract information about what's going on in my study area, and the geometric of the image can allow us to extract information about where and how the spatial evolution of my object of study is. We can consider two main groups in relation to detection strategy. On the one hand, the detection methods based on the spectral signature or based on experts, which have these features. The spectral signature of the target is assumed to be known. The task is to detect all the pixels whose spectrum shows a high degree of correlation with the one used as a reference. The reference spectrum is usually a reflectance measurement taken in the laboratory, and performance may be limited by uncertainties introduced by radiometric calibration, atmospheric compensation, acquisition geometry, signal contamination by adjacent materials. And on the other hand, automatic detection methods, which have these features. No a priori knowledge of the target's spectrum is assumed. The task is to identify pixels whose spectra differ significantly from a spectral background. For example, anomaly detection methods can be implemented in raw data since it does not require biophysical parameters as reflectance, emissivity, temperature, etc., in absolute scale. But what is image spectrometry? What's the difference between other remote sensing techniques? In image spectrometry, also named hyperspectral remote sensing, the objective is to extract a spectral signature from each image pixel that describes the spectral response of the pixels and its spatial location. We can then use the pixel spectral signature as a search pattern of the rest of the image, or compare into other spectra from spectral libraries. Image spectrometry has a close relationship with planetary prospecting. It has been shown as a powerful technique to analyze the composition of materials and their condition remotely. The analysis of the position, shape, and depth of the spectral signatures of each pixel of the image allows us to obtain information about the composition and condition of the materials. So allows us to detect this particular material and separate it from other materials. We can see in this slide the main airborne image spectrometers or hyperspectral sensor. I want to point out the different spectral ranges where these sensors acquire data that we can observe in the x-axis here. This fact is not accidental and obviously responds to the application for which the sensors have been designed. To study water, mineralogy, forest, agriculture, etc. Next, after this brief introduction about remote sensing and image spectrometry, I'm going to talk in part about the research presented at the last Congress of the International Society for Remote Sensing and Photogrammetry that took place last June in Nice, France, developed work together with my colleagues from France, Peru, Brazil, and Costa Rica, which name you can see here. One of the study areas that I am presenting is the Turrialba volcano, located in the central volcanic range of Costa Rica in Central America. Our research is based on image spectrometry and in situ measurements through two different strategies, an expert method, basic method, and automatic methods. And it's supported for previous results using airborne hyperspectral data for the master and HIMAP sensors of 2005, as we can see in this slide. We can see here the diagnostic bands, sorry. Sorry, we can see here the diagnostic band, too highly reflective and too highly absorptive, used to detect volcanic activity, in this case, the hydrothermal alteration activity of the volcano for each airborne sensor, HIMAP and master. For this study case, we use data from Sentinel-2, ALI, and Hyperion sensors for 2013, 2017, and 2018. The channels that presented a high signal noise radio had been rejected. The satellite images had been atmospherically corrected and geometrically. Image exploratory techniques had been applied with the aim to contrast biophysical parameters and obtain a first approximation of the state of vegetation and soils in the Turrialba volcano region. Here we can see some examples of color combination and vegetation indexes. Let's turn now to the methodology of hydrothermal alteration detection. We have applied two research strategies by three different techniques, as I said. One based on expert knowledge and two automatics. The first one is a principal components analysis through a technique named cluster. We have chosen 4 wavelengths for generating a different PCA, 2 highly reflected and 2 highly absorptive for each mineral. We mainly analyze it, clay minerals and iron minerals. The results are strongly influenced by vegetation cover. A good example of this is the well-known color combination for minerals we can see in this picture. Another technique that we have applied to study volcanic activity is an automatic technique named anomaly detection. A spectral anomaly is a pixel response that is strongly different from a spectral background from a statistic point of view. Anomaly detection is often a first analysis step to obtain region of interest with potential targets. This technique has many applications in different areas such as defense and security, military target detection, anti-personnel mine detection, engineering and environment, water stress location, pathologies in materials, forest location in affected trees, fires, natural disasters, search and rescue operations, pollution detection, geology and volcanology, rare mineral detection, volcano activity monitoring, and archaeology, detection of semi-buried remains, for example. In anomaly detection, a multidimensional sample vector is used for render the pixel on the text put, and a binary hypothesis of the text problem. The pixel on the text is a background pixel, or the pixel on the text is a target anomaly pixel. To compute that, in anomaly detection, we use the Neyman-Pearson criterion that describes the optimal statistical criterion to distinguish two simple hypotheses. In anomaly detection, our target is detected based on the measurement or calculation of the difference between a put and the spectral background. Anomaly detection can be grouped in two large categories according to the strategy of the measurement of the spectral background. So we have global anomaly detectors. The spectral background is defined by adopting all the pixels of the image or a large part of it as a reference, and local anomaly detectors. The spectral background is defined by the pixels of a small pattern with window around the put. Within these two large groups, there is a wide variety of anomaly detection methods. In this table, Manolakis in 2004 summarized the main anomaly detection methods to date and their main features, as we can see in this slide. And on the other hand, automatic detection methods which have these applications, for example, in volcanoes areas. We have built on previous work testing different anomaly detection methods with good results. We can see three scenarios: two volcanoes in tropical areas and one in Maine, USA, where the spectral anomalies were related to the volcanic activity and mineralogical composition. We use for that unmanned vehicles, and we can see some of the examples of the mapping generated. Anomalies obtained for red and CLE algorithm that's well known in the scientist community had been verified by a method based on projection pursuit. We can see some examples of minerals of hydrothermal alteration for the Turrialba volcano. We have analyzed the relationship between the detection of hydrothermal alteration and spectral anomalies here. obtained by different methods for the Turrialba volcano, based on previous work, such as the one offered by the image we can see, with a strong statistical relationship. The third technique that we have applied is the discrete spectral profile analysis, based on a pattern meaning technique adapted here to handle the spectral profiles. It uses the spectra of the pixels of the multispectral and hyperspectral images, and in these discrete spectral profiles, it finds local shapes that are shaded by a significant number of pixels. Each selected local shape is then visualized using an occurrence map, where highlighted pixels represent the pixel containing the local shape in their spectral profile. We can see some examples of occurrence map for Sentinel-2 corresponding to clouds up and vegetation down. Here, we can see the calculated spectral anomalies of the 4 images used. In black, strong anomalies. And here we show the results of the regression models with a moderate relationship between spectral anomalies and hydrothermal alteration. The R-squared statistic indicates that the best adjusted model explains 22% of the variability in hydrothermal alteration and spectral anomalies. We have performed a validation of the results obtained remotely from image analysis. The accuracy of the detected hydrothermal alteration has been studied. For this, an in situ validation campaign has been carried out with a result of 33 points, of which the mineral composition and spectral signature has been measured. The hydrothermal anomalies and alteration detected from Sentinel-2, Ali, and Hyperion in Turrialba and surrounding areas are linked to the volcano activity, mainly in the crater, to crops and bare soils, and as well as artificial surfaces, mainly building roofs. We can also study the volcanic activity and the land deformation it produces due to its effects. In order to do that, we have applied SAR differential interferometry. We can see in the slide one of the most paradigmatic cases of application of this technique in the earthquake of L'Aquila, Italy, which took place in 2009. DINSAR needs data from a particular radar sensor named Synthetic Aperture Radar, SAR. That is a remote sensing active system that works in the microwave spectral range. We can see here in this table the name of the main bands used in SAR, LSCXKU, and their wavelengths. In this slide, we can see one of the most well-known spaceborne SAR systems and their radar band uses. That here. To do interferometry, we need 2 SAR images that illuminate the same target with the same mode, with similar viewing angle. The hypothesis is that the study object has not changed between the 2 SAR images, and that the possible change that can be detected is due to a deformation in the vertical axis, land subsidence, for example, or in the X and Y axis. We can see in this slide the mathematical basis of DINSAR that allows us to extract the phase component of the interferogram due to the movement or deformation here. This is the usual task flow in DINSAR. We must do polarization and resampling. We need a digital elevation model assisted for coregistration. We must compute the interferogram between the master SAR image and the slave SAR image. We must do filtering, geocoding, and wrapping, and finally we must project the interferogram into the Earth. We have applied DINSAR to analyze the impact and deformation of the land deformation due to effects of the eruption of the Fuego volcano that took place on June the 3rd in 2028. 30 kilometers from Guatemala City. If we make a zoom, we can observe the coherence and interferogram compute for this eruption. Each change in the color table corresponds with a subsidence of 1.5 centimeters approx. Finally, we have applied the same methodology to analyze the volcanic activity due to the eruption of the La Palma in Spain that took place the 13th of August in 2021. We have compute thermal anomalies using Aster data. We can see an infrared color combination of Aster RGB 231 for the island of La Palma, and the thermal global anomaly detail in grayscale here, where black pixels are strong thermal anomalies. This strong thermal anomaly corresponds with the big seismic events that occurred from 11th August and to the 19th August. We also have analyzed land deformation due to the volcano eruption. We can see in this picture the vertical deformation in millimeters in the period August 11 to October in 2021, measured at global navigation satellite systems, stations, and average vertical deformation by DINSAR points in 500 meters buffer of land stations. In blue, we can see global navigation satellite systems measurements, and in red we can see DINSAR average of the deformation due to the eruption in La Palma. We can see here a detail of the thermal anomaly detection result for La Palma volcano eruption. In an analogous experience of the Turrialba volcano, the grid thermal anomaly computed that we can observe in this profile has a relationship with the final eruption location of the volcano. That means this technique could be a good tool to monitoring the volcanic activity. Some conclusions. The characteristics of high-resolution data in both spatial and spectral for natural cover has been studied by different remote detection methods using Aster, Ali, Hyperion, Sentinel-2, and Sentinel-1 test data sets in 2013, 2017, and 2018 and 2021 dates. This talk evaluates the performance of detection methods of hydrothermal alteration materials and land deformation in multispectral and hyperspectral scenes with similar backgrounds in the Turrialba volcano in Costa Rica, in La Palma volcano in Spain, and the Fuego volcano in Guatemala, through two different strategies whose main future interest lies in the automatic identification of patterns of volcanic activity without prior knowledge or poor information about the area. Higher concentration of some hydrothermal alteration materials in various areas where the source of error are minimized, mainly clouds and vegetation, are correlated with the spectral anomalies in the visible and near infrared and the thermal infrared spectral range. The spectral missing associated directly with the spatial resolution has an impact in a significant way on the characterization of the tropical volcanic backgrounds that is critical to compute spectral anomalies. Okay, that's all. Muito obrigado. Thank you very much for your attention. I will be happy to answer your questions. You can ask me in Portuguese if you want, and I can answer in Spanish.
Okay. Thanks a lot, Dr. Juan, for your very interesting presentation. You combined several different remote sensing sources, and you provide examples, very interesting examples. We have two questions that are written on the chat. I'm going to read the questions, and if you, one of the questions are written in English, so it's easy for us to share with you. The first question.
Where are the questions, please? Where are the questions?
The chat.
In the chat.
Yeah.
Where is the
but
chat?
I'm going to read. Anyway, I'm going
okay.
to read the question for you. Thanks for your presentation. And then the question is, hydrothermal materials are common in most volcanoes or not? The questions is regarding if hydrothermal materials are common in volcanoes.
Yes, are common in volcanoes, in ancient volcanoes, and in the sea depth, in the ocean depth too, because hydrothermal alteration materials need to be for the presence of water and high temperature.
Okay.
Need for this kind of minerals it needs the presence of water, and for this is a good point to planetary prospection, because if you detect for example, in Mars, hydrothermal alteration minerals. In Mars, for example, you are detect water,
Okay.
maybe in the past, obviously.
Understood. We still have some more questions and we have still a little bit of time. So the second question is, good morning, Professor Juan. Is there a lot of difference between tropical and extratropical volcanoes?
Yes, of course. When you are using remote sensing data and image spectrometry, you are working with this kind of data, there are a big source of error, that is the vegetation, clouds and vegetation. And clouds and vegetation are often in tropical scenarios. It's for that we use the active systems to how do you say that in English? To study best this kind of scenarios, of tropical scenarios. Okay.
Okay, thank you. Still have one more. Para estudo de materiais. When you are going to study the hydrothermal materials, what kind of satellite data do you use or do you recommend to study the hydrothermal materials?
Okay, there are good questions. All. Yes, the best sensors to study hydrothermal alteration are the image spectrometers or hyperspectral sensors.
Okay.
They are the best because you can extract a full and a very accuracy spectral signature from this kind of data, from hyperspectral sensors. And if this kind of sensor are airborne sensors, is the best solution, because airborne sensors provide us a very quality data and a very good spatial resolution. But you must acquire data in the sphere spectral range, in the short wave infrared range, spectral range, because in this range is the best spectral range to study the hydrothermal alteration materials. You need a good spatial resolution, airborne sensors. You need a very good and high spectral resolutions, image spectrometers or hyperspectral sensor, and you need a very good spectral resolution in the short wave infrared range, spectral range.
Okay, thank you. There is a final question here. It's written in English. I'm going to read for you. The question is the following. The automated identification of patterns of volcanic activity may be predicted using artificial intelligence techniques, for example, recurrent neural networks. What is your opinion about this? If the automated identification of patterns of volcanic activity can be predicted using artificial intelligence.
Okay, it's a good question too. Yes, we can apply intelligent artificial as of course. I have a good a good opinion about intelligent artificial, but it's a little bit complicated because I don't know, but in several experiences, the intelligence artificial cannot apply, cannot, how do you say that in English? Cannot move to other scenarios or to the other applications. The results for a particular scenario, a particular application of from intelligence artificial, in my opinion, sometimes cannot move to other scenarios or to other applications. I don't know if you can understand.
It's a
more or
common
less.
problem to apply the artificial intelligence from one domain to the other, right? Or sometimes even changing the region, the algorithm will not work properly.
But in my opinion, it's a very good agreed tool. Of course.
Okay, we still have one more question, and since we have 5 minutes to the next, I'm just asking for all the participants to click on the link to sign that you are present during this talk, okay? And if you still have questions, there's a link in the chat and also at YouTube. But let's consider this last question from Vitor Curtarelli. The other ones I didn't say the name because it was written on the slide but anonymously. In this case, did you use Sentinel-1 data during the research? And the second question is, did you use SNAP, S-N-A-P, the platform, to pre-process and interferometry process? And the third question is, what programming tools do you recommend for this kind of tasks?
Okay, a very good question too. Yes, of course. We use Sentinel-1 from Copernicus European program that is public and free. But we use all of them, all of radar data, of SAR data that we can use. We can, and of course, Snap software is. We use Snap for differential interferometric SAR processes, and in my opinion, it's a very, very good software to do that because it's free and it's public. And the best, but we use two MB software,
Yes.
and MATLAB to yes, there are the main software that
Okay.
I use to. Okay.
Okay, so I think we finished our questions. We are also on schedule. I would like to say thank you again, Dr. Juan. It was a pleasure for us to receive your presentation in our event. I think we are done. If you want, you can check at our chat once again just to check
Okay.
if someone else are going to make some questions, but I think we finished our questions. Okay, thanks a lot. We are going to move on for the next presentation. Thanks a lot.
Okay.
Thank you.
Thanks the same for me. Muito obrigado.
Muito obrigado. Okay. Rafael, você quer falar alguma coisa? Posso continuar?
No, just like to thank you. Thank you very much for the presentation. Just that, please go ahead.